Hello. In this video, I'm going to show you how to use partial fraction decomposition to integrate. Now, usually when you're using partial fraction decomposition, you have a fraction in your integral, and really it needs to be a polynomial over a polynomial where the denominator is factorable. And what you're going to want to do is break that fraction into multiple simpler fractions that are easier to integrate. It's the whole idea behind this method. Now, there are three different cases of what that denominator might look like, and that would tell you how the fraction breaks down. The first case is where you have distinct linear factors. So distinct meaning different, and linear meaning that they were totally factorable. There's no quadratics left after you've factored as much as possible. So here's an example. I've got some polynomial r of x at the top, and then the bottom has factored into these two distinct linear factors. However many factors are in the denominator, that's how many fractions it will break down into. So I have two factors, so it will break down into two fractions. And because they're distinct and linear, I know that the numerator is going to be some constant. I just don't know what that constant is. So that's the second step, is to actually solve for those constants. The first step here is just to know how it breaks down. The second case is repeated linear factors. So maybe I have a factor that has an exponent on it, like this one here that has a cube. So I have four factors down here. There's the 2x minus 1 and then 3 of the x plus 3's. So this is going to break down into four fractions. And how those denominators break down is I have that distinct linear factor by itself. And then the repeated linear factor, you're going to have every power of that factor, starting at 1, going up to the power that shows up on the left here. So this is a third power, so I have x plus 3 to the first, to the second, and to the third. If it had been to like the fourth on the left side, then I would have had another fraction with an x plus 3 to the fourth there. And just like with the first case, the numerators are going to be constants for each one of these. The third case is where that does not happen. So with an irreducible quadratic, so for example, here I have x squared plus 3. It's not factorable, and so this is just factored as much as possible. And the consequence of that irreducible quadratic is that there's a possibility I have more than just a constant in the numerator. It could possibly be some kind of binomial. There's no guarantee. I might solve for these constants a, b, and c, and b ends up being 0, and that's fine. But there's always a possibility, so we have to put that in there as a binomial on the top. So again, I have the linear distinct factor with just a constant over it, and then the irreducible quadratic has a binomial in it. So those are the three cases that we're really going to focus on. We're going to do a couple of examples, and then I'll leave one for you to try on your own. With this first one, and it looks like some of my animations didn't work, sorry. So I have dx over x squared minus 4, and that denominator factors as a difference of two squares, so an x minus 2 and an x plus 2. And so they're distinct linear factors. So this fraction 1 over x squared minus 4 from the integral is going to break down into a constant over each of those factors. So two factors means two fractions. Now I have this set up where they're equal to each other, so I'm going to treat it like a rational equation and solve it by multiplying by the least common denominator, which is the x squared minus 4. So both sides of this equation get multiplied by x squared minus 4. And then I simplify, and after I'm all done simplifying, I shouldn't have any fractions left over in this equation. On the left side, the x squared minus 4's cancel, and I have just 1. And on the other side, one of the factors cancels with each fraction as I distribute it. So I end up with 1 equals a times x plus 2 plus b times x minus 3. Okay, so the part that didn't cancel with the bottom gets multiplied by the constant on top. Okay, so remember our ultimate goal here is to solve for a and b. And so what I'm going to do is distribute to simplify everything on the right. And then I'm going to start collecting like terms. For instance, I have an AX and I have a BX, and on the left side, I have no X term. And these two sides have to be equal. So that means that these two X terms would have to add up to 0 in order to match the lack of an X term on the left side. Then I also have a 2A and a minus 2B. And those are constant terms because there's no X there. So those are going to have to add up to equal the constant term of 1 on the other side. And so I can group this if it makes it easier. This is an optional step here to kind of see that I grouped the X terms together and factored the X out, and then I grouped the constant terms. And you can see which ones have to match up with the other side. So from this, I get a system of equations. So A plus B has to equal 0 since there is no X term on the left side. And 2A minus 2B has to equal the constant term of 1 on the right side. And so now I have the system of equations. No X's are in there anymore. And I'm going to solve this using those old methods from algebra. I can either do a substitution method or an elimination or addition method here to solve this. So A plus B equals 0, 2A minus 2B equals 1. So what I'm going to do is multiply the first equation by 2, and then I'll add that to the second equation, causing the B's to cancel out here. So if I multiply by 2, I get 2A plus 2B equals 0. Adding that to the other equation, the B terms cancel out, and I get 4A equals 1, which solving for A gives me a 1/4. Now I can take that A equals 1/4 and plug it back into either one of the original two equations. I chose the first one because it's simpler. And replace A with the 1/4 and solve for B. So I get B equals negative 1/4 over here. Going back to the partial fraction decomposition that we started out with, well, now I know that our original fraction breaks down into this 1/4 over x minus 2 minus 1/4 over x plus 3. And then I can finally, now that I've done all that algebra, I can go back to the integral and break that down. So I'm going to throw the constants of 1/4 out front, and now I have these two integrals that are simpler than what I started with. And I can integrate those. Technically, I'm doing a u substitution here, but u is going to be x minus 2 or x plus 2 in each of these, which gives me dx equals du. So I did kind of skip some of the steps there, which is usually fine to do when the derivative of whatever u is equal to is just going to be 1. So integrating that, I got the 1/4 out front, and then 1 over x minus 2 is going to give me the natural log of the absolute value of x minus 2. And then the same thing for the second one, plus my constant of integration. So there is the solution to this using partial fraction decomposition. One more example I want to go over with you before I turn you off on your own. This one's a little bit more complicated. I still have two factors in the bottom. This one's factored completely already. But one of them is an irreducible quadratic, this x squared plus 1. So that means when I break this down, it's going to break into two fractions, and that irreducible quadratic possibly has a binomial in its numerator. Just like before, I set the two sides equal to each other and solve the rational equation. So multiply everything by the least common denominator, which is the x times x squared plus 1. So both sides get multiplied by it, and a bunch of stuff is going to cancel. So the a over x, the x's will cancel, and the a will get multiplied by x squared plus 1. And then the bx plus c is going to get multiplied by the x in the second fraction. So I end up with an equation that looks like this. And just like before, I'm going to start distributing and collecting like terms and matching them up on each side of the equation to get my system of equations. So distributing, I get ax squared plus a plus bx squared plus cx on the right. Now I can see I've got two x squared terms on the right and no x squared term on the left, so those are going to add up to 0. There's just the one c term, so it's going to have to match the coefficient of the x term on the left side, and then the constants will have to match as well. So I end up with this system of equations. And the nice thing here is 2 of my variables are already solved for just through doing that. So to solve for the one variable I don't have, the b, I can take a equals 3 and substitute that into the first equation to solve for b. So 3 plus b has to equal 0, which means that b equals -3. So now I know what each of my variables is, and I can write out that partial fraction decomposition, and it looks like this. And now I can take this back to the integral and see how I'm going to integrate that. So I went ahead and broke it up into 2 separate integrals, one for each fraction. The first one is just going to be a natural log, not too difficult there. The second one is a little trickier. I'm actually going to break this up again into 2 separate fractions. Because I have a binomial in the top, I can rewrite each term over the denominator. So I have the -3x over the denominator, and I went ahead and pulled the -3 out front, and then the -1 over the denominator. And I did that because I'm going to integrate each of these differently. The middle one here, I can solve using a u substitution. The third one is actually going to be a formula that is absolutely worth memorizing. Okay, so for that middle one, a u substitution is going to work where the entire denominator is u, making du equal to 2x dx. And since I have an x on the top, that makes this all work out nicely for us. So I go ahead and do my substitution for that one and then integrate. So 3 over x gives me 3 natural log of the absolute value of x. And then du over u is going to give me the natural log of the absolute value of u. And remember that this 2 was not present in the integral, so I had to divide by 2 out front to make that substitution work out. And then the last one I mentioned was a formula. When I have 1 over x squared plus 1, that is just tangent inverse. And actually, that's a typo right there. That should just be tangent inverse of x, not x squared plus 1. Okay, so we're almost done. Last thing to do is reverse the u substitution in this middle term here. And so doing that, I end up with an x squared plus 1. And you'll notice that I dropped the absolute value because x squared plus 1 is always positive. So it's not really necessary to have the absolute value there. It's fine if you leave it there, but you can leave it off and you'll be fine in this particular case. So this is my final answer, although I did have that typo here with the tangent inverse. That should just be tangent inverse of x right there. And there is my final answer for this one. Okay, so the only example we haven't done is one with a repeated factor. So here's an example to try on your own. Use the guided notes to kind of take you step by step through the solution and see how it goes.